All right, so we are going to do some differentials. All right, so number 6 only has an a and a b to it. So consider the differential equation, dy dx, blah, blah, blah. Let y equals f of x be a particular solution to the differential equation that passes through the point 1, 0. Part A, write an equation for the line tangent to the graph of f at the point 1, 0. Use the tangent line to approximate f of 1.2. All right, so we know that we need a point and a slope. Okay? So our point is going to be 1, 0. Our slope we're going to get by plugging 1, 0 into our dy dx. So e to the y times 3 x squared minus 6 times x. Now e to the 0 is just 1. 3 times 1 squared is 1 minus 6. So we end up with negative 3. So our slope is negative 3. So your equation is y minus 0 equals negative 3 times x minus 1. Now remember, when we're doing local linear approximation, you're going to change this to be a fancy y, which is f of x, and then you're going to, well, you would add this over, but it's 0, so we're not going to add it over. So we end up with f of x is equal to a negative 3 times an x minus 1. Now, if you want to evaluate or estimate that at 1.2, you put in a 1.2. 1.2 minus 1. Now I've already put that in my calculator, and I ended up with negative 0.6. Okay, local linear approximation using differentials. All right, part B, find y of f of x, the particular solution to the differential equation that passes through 1, 0. So we want to separate our variables. We want to put the dy and the y's together. We want to put the dx with the x's together. So I'm going to have dy divided by e to the y, and I'm going to have a 3x squared minus 6x and then the dx. Now I'm going to have to integrate both sides, but I need this to be at the top when I integrate. So I'm actually going to be integrating e to the negative y dy, and I'm going to integrate 3x squared minus 6x dx. Now, my u substitution, that would be negative y. So du dy is equal to negative 1. So essentially this is just negative e to the u, the integration of negative e to the u du. Integration of e to the u is just e to the u. So I'm going to get negative e to the u. My u is negative y. And then over here, 3x squared would become 3x cubed over 3. So that's just x cubed. This would be 6x squared over 2. So that's 3x squared. And then your plus c. Okay. Now, it says that we're evaluating this at the point 0, 1. So what I'm going to do is plug in my 0 and my 1 to this point. So my, oh, it's 1, 0. Let's get the point right first. 1, 0. So I'm going to plug the 0 in, and I'm going to plug the 1 in, and I'm going to solve for c. So e to the 0 is 1, so this is negative 1. 1 cubed is 1, minus 3, plus c. So that's a negative 2, add 2 over, I find out that c is equal to 1. All right, so now I got to rewrite this equation. So the equation that I was going to use before I plugged in the 1, 0, and I got to solve for y. So I have negative e to the negative y is equal to x cubed minus 3x squared plus c, which in this case is 1. Now, I can't do anything with that negative there, so I need to get rid of that negative first. So basically I'm just dividing the whole thing by negative 1. Now that I have that, I can do an ln of both sides. Now, the reason I do the ln both sides is because remember I want that exponent to come out of the exponent spot. ln's allow me to bring it to the front. So I end up with negative y ln of e equals the ln of negative x cubed plus 3x squared minus 1. Okay? I put absolute values. You'd be okay if you made them parentheses as well. However, remember you can't have the ln of a negative number, so it needs to be positive anyway. Now ln of e goes away because that's just equal to 1, and now you're going to divide by a negative. So y is equal to negative ln of negative x cubed plus 3x squared minus 1. And you're done. That's your final answer right there. Okay? All right, moving on to number 5. Number 5. So, looking at that one. The current rate at which a baby bird gains weight is proportional to the difference between its adult weight and its current weight. At the time t equals 0, when the bird is first weighed, its weight is 20 grams. If b of t is the weight of the bird in grams at time t days after it is first weighed, then db dt is equal to 1/5 times 100 minus b. Let y equals b of t be the solution to the differential equation with the initial condition b of 0 equals 20. Woo! Lots of fun words there. Let's look at part A. Is the bird gaining weight faster when it weighs 40 grams or when it weighs 70 grams? Explain your reasoning. All right, well, I'm having trouble. dB dt, that's the rate at which the baby bird is gaining weight. Okay? Remember, when we did related rates, whenever I said find the rate of the volume or the rate of the area or the rate of the radius, we always made it d whatever it was. So like if it was the rate of the area, we made it dA dt, because rate stands for derivative. So if you want to know which one's gaining weight faster, you're going to plug those numbers into the equation and see which one's bigger. Okay? So for 5a, you get dB dt is equal to 1/5 times 100 minus 40. Okay? And you get 12. Then you get dB dt equals 1/5 times 100 minus the 70. And you end up with 6. Okay? So, this bird is gaining weight faster at 40 pounds than it is at 6 pounds because the rate at 40 grams is higher than the rate at 70 grams. Okay? So, all right, gaining weight faster at 40 grams since the rate of growth is higher. Okay? So as long as you show your work, as long as you make a final statement, then you're good to go. Alright, let's take a look at part B. Part B says, find the second derivative, and then use that second derivative to explain why the graph of B cannot resemble the following graph. Alright, so dB dt is equal to 1/5 times 100 minus b. Now I'm going to go ahead and distribute that first, and when I distribute it, that's when I'll take the derivative. So 1/5 times 100 is just going to be 20 minus a 1/5 b. So I'm going to go ahead and take the derivative of that. So dB squared over dt squared is going to be, well, the derivative of 20 is nothing. The derivative of this is a negative 1/5, and don't forget your differentials, your implicit differentiation, dB dt. So you need to plug that stuff back in. So that's going to be negative 1/5 times your 20 minus 1/5 b. Or negative 4 plus 1 over 25b. So there's your second derivative. Now, the question says, explain your reasoning of why the graph of b cannot resemble this following graph. So how come this graph isn't right? So they're telling you the graph's not right, because it says why it cannot resemble it. But why isn't it right? What's wrong with it? Well, you need to think about what you just found. You just found the second derivative. And what does the second derivative tell you about? The second derivative talks about concavity. Okay? So it talks about concavity. So what we need to do is we need to figure out what's going on with this concavity here. Now take a look at your B. Your weight in grams in their graph is going to go from 20 to 100. Okay? So we kind of want to look and see what happens with our second derivative graph between 20 and 100. Now one thing that I did is I was like, I wonder what my pip is. I wonder what my possible inflection point is. So if I set this equal to 0, I'm going to add 4, and I'm going to multiply by 25, and I find out that b is equal to 100. So 100 is actually my pip, my possible inflection point. So if it's my possible inflection point, that's where I'm going to change concavity. So that doesn't make sense. That kind of implies that I'm going to be the same concavity over here altogether. Well, let's find out. Like, we got to plug in something between 20 and 100. So, I don't know, let's plug in 40. 50. You could plug in 50 because 50 is nice and easy. If you plug in a 50 right here, 50 over 25, well, that's just going to be a 2, which means it's going to be negative. Okay? So no matter what you plug in over here, until this thing's 100, it's going to be a negative sign. And then when you flip over here and you make it bigger than 100, let's say 101 or, 200, anything bigger, that's when it's going to change over to be positive, which means the graph should be concave down between 20 and 100. But take a look at your graph. Right here, you're concave up, and then you're concave down. So, you just say the graph of B should be concave down from 20 to 100, and a portion of this graph we'll say B is concave up. Okay? So just think about when they're trying to tell you to analyze something, think about what it is that you know and what it is that you can find from that information. Looking at the graph, we're like, usually we want to plot points, but we don't have the function. So we can't plot points if we don't have the function. So think about what it is they had you find and what you know about that thing in order to then figure out what was wrong. You knew concavity comes from second derivative. So if you analyze the concavity, maybe you'll come up with something. Okay? All right, part C. I'm going to flip the paper over here. Part C says use separation of variables to find y equals b of t, the particular solution of the differential equation with initial condition of b of 0 equals 20. So we have db dt is equal to 1/5 100 minus b, and b of 0 equals 20. All right, so I got to separate my variables. Now, this 1/5, I'm going to leave it over here with my dt. Remember I told you it's easier. Now, could you bring it over here? Of course you can, but it just might make your work a little bit more complicated. So I'm going to have db over 100 minus b. I cannot separate those because we're not adding and subtracting. We're only multiplying and dividing. And we have 1/5 dt. And I'm going to integrate both of those sides. Okay? So my u is 100 minus b. So du dB is equal to -1. So I'm integrating 1 over u times a negative du. Well, that tells me that I'm ln of u with a negative in front. So negative ln of 100 minus b equals 1/5 t plus c. All right, so they told me that b of 0 equals 20. So negative ln of 100 minus b, which is 20, equals 1/5 times 0 plus c. So negative ln of 80 is equal to c. All right, so if I rewrite this, I have negative ln of 100 minus b is equal to 1/5 t minus an ln of 80. This looks ugly, but just keep going through with what you know what to do, and things will work out. Now we can't do our change our ln to log base e until we get rid of this minus sign. So we have the ln of 100 minus b is equal to a negative 1/5 t plus an ln of 80. Now, this could be log base e, and I can do my log loop thing. So I have e raised to the negative 1/5 t plus ln of 80 equals the 100 minus b. I'm trying to solve for b here. Now, this, I can separate this into e to the negative 1/5 t times e to the ln of 80. Well, think about what happens to that. That's just going to become 80. So I end up with 80e to the negative 1/5 t. Now, what I just did is I solved for that big C. Okay, remember that big C that we put in the front? Well, I went ahead and I plugged my value in first, found my C, and then I'm finding big C later. Could you do the big C thing and plug in those numbers? I'm sure you probably could. I didn't, but go ahead and give it a shot. And if you have a question about that, I'd be happy to answer it and look at it. I just didn't do it when I was doing my work. Now we got to make sure that we're solving for B. So we got to subtract 100. But then you got this negative b, so you're going to end up with negative 80, e to the negative 1/5 t plus 100 is equal to b. And that's your final answer. Okay, negative 80, e to the negative t over 5, or negative 1/5 t plus 100. All right, does that finish number 5? It does. All right, so let us take a look at number 6. All right, number 6, they give us this equation first. And they ask us to show that the derivative, dy dx, is equal to negative the quantity of x plus 1 over 2, the quantity y cubed plus 1. So we get to do implicit differentiation. So we get a little practice with implicit differentiation. Remember, when you're implicitly deriving, if you're deriving something that's not an x, you've got to do that d whatever over dt. So this is 2x plus 2. Those were x's, so I could just take the derivative. The derivative of 4y to the 4th is 4y cubed. Don't forget your dy dt. Oh, it's dy dx, because we're doing it in terms of x. Oh, dy dx. Plus the derivative of 4y, which is 4. dy dx equals the derivative of 5 is 0. Now, these two things are going to move on to the other side. These two things, I'm going to pull out my dy dx. So I got 4y cubed plus 4 equals a negative 2x minus a 2. Now I just have to divide by that. Now at the same time of dividing, I'm going to pull out my GCF here. So I'm going to pull out a negative 2 here, and I'll be left with x plus 1. I'm going to pull out a 4 here, and I'll be left with y cubed plus 1. And my 2 and my 4 can reduce. And you see that we have ended up with the equation they wanted us to end up in the first place. Now, make sure that you end exactly as they tell you to. And remember, since they gave you the answer, really it was all about the work. You're going to get points for showing that you know implicit differentiation, and then points for solving and getting the right answer. This is probably a 2-point question right here. All right, so our next thing, part B, says write the equation for the line tangent to the curve at the point -2, 1. So we need our point, which they gave us, -2, 1, and we need our slope. Well, now even if you couldn't solve part A, they gave you the correct derivative. So even if you get stuck right here, don't use your wrong answer. Go ahead and use the right answer so you can get B correct. So your slope should be negative, and then the x plus 1 over the 2 and the y cubed plus 1. So I'm just plugging the point into the derivative. So when I plugged the point into the derivative, I found out that my slope was 1/4. So I got y minus 1 equals a 1/4 times x plus 2. Done. Okay, that's probably a 1-point question. You didn't have to do a whole lot of stuff, you just really needed to find the slope and recognize that in order to get the equation of the tangent line, you need a point and a slope. All right, moving on to part C. I think I have enough room right here. Part C says find the coordinates of 2 points on the curve where the line tangent to the curve is vertical. All right, denominator equals 0 for a vertical line. So we're looking for where the denominator of the derivative is equal to 0. So the denominator of the derivative was 2 times y cubed plus 1. We want to set that equal to 0. All right, divide by 2, you get 0. Subtract 1, you get y cubed is equal to -1. So y is equal to -1. All right, now they actually wanted the first 2 points. This is worth 1 point on our free response, but they want the x values of these as well. So in order to find the x values of these, we got to plug them into our original equation. So our original equation is x squared plus 2x plus y to the 4th plus 4y equals 5. You know that y is equal to -1. X squared plus 2x plus the -1 to the 4th plus 4 to the -1 equals 5. So I did the math, and a +1, because -1 to the 4th is +1, minus a 4, and then equals a 5. When I put those all together, you should get a -8. And then I was able to just factor that. So I got x plus 4, x minus 2. So x is equal to -4 and a +2. So my 1 point is -4 and a -1. My next point is a 2, -1. So that would give me my full answer when I have both of those. Okay? I feel like we did maybe even this exact problem on a test, or maybe I had a portion of it, and maybe one of them was extra credit. I don't remember, but I do remember doing this kind of problem at some point. Let's look at part D. This was on an no, I think it was just on a test at some point as well. Part D says, is it possible for the curve to have a horizontal tangent line at points where it intersects the x-axis? All right, well, it's going to intersect the x-axis when y is equal to 0. That's something that's important to do. Now, it's going to have a horizontal tangent line when the top of the differential equals 0. All right, so let's set the top of the differential equal to 0. So negative the parentheses of x plus 1. So you end up with x equaling -1. All right, so is it possible? So at x equals 1 is where you're going to have a horizontal tangent line. But is it possible that it is on the x-axis? Well, go back to your original equation. When x equals 1, in order for it to be at the x-axis, y would have to be equal to 0. So if you plug in a -1 in for your x's, and you plug in a 0 for your y's, does that equal 5? Well, -1 squared is 1, minus a 2, and that does not equal 5. So the answer is no. Okay, now, when they say explain your reasoning, well, right here, we just explained our reasoning. When we plugged in the -1, and we plugged in the 0, because we even described it right here by saying they intersect the x-axis when y equals 0, horizontal tangent line when the top is equal to 0, and we went ahead and we showed our work. That was part of our explanation. So we're good to go there. All right, our last one, number 5. So they gave us our differential dy dx is equal to 1/2 x plus y minus 1. All right, now, instead of going ahead and taking the time to make this whole thing, I'm just going to show you the one that I already did. It makes it a little bit easier. I don't know how they would make you do a slope field, just because, I mean, you could do it just like I did here, but I find that usually they probably won't do that, just because they would want to have the points on the paper already for you. However, let's look, because we never know what they do. So notice over here, the only way I could tell the slope of all these things is to actually plug in all the points. So it's a time-consuming question where they don't give you a whole lot of points for it. But it's also not hard. So if I plugged a 0, 0 into my differential, I had 0 plus 0 minus 1. I found out the slope was -1. So I estimated what a -1 slope would look like. Then I went over to the point 0, 1. So I went up here. Well, so that was 0 plus 1 minus 1. So that gave me a 0. So I have my horizontal tangent line. Then I used the point 0, 2. So I had 0 plus 2 minus 1. I found out my slope was 1. So I made a +1 slope. Now I continued on with every single point, getting the slope for each one, and then drawing something that was pretty similar to what I thought it would be. Okay, if this is a 1, sorry, -1, this was a -1/2, so it was a little less steep. This was a -1.5, so it was a little more steep. Now again, they're not going to be particular, but they do want to see a little gradient. They don't want to see that -1 and -1/2 are the same. They need to be a little bit different. Okay? So there is our slope field. So let's move on to part B. Part B wants you to find the second derivative in terms of x and y. Describe the region in the plane xy that shows which all solution curves to the differential equation are concave up. So where is this thing concave up? So this one was a toughie. This whole question actually was a pretty tough one. Past A and C were okay. And finding, it was okay. D was the one that was impossible. Let's take a look at B. Finding the second derivative. And that's not so bad. So finding the second derivative, the derivative of 1/2 x is just 1/2. The derivative of y is going to be dy dx, and the derivative of 1 is just 0. Okay, so I needed to plug in my dy dx, so I ended up with 1/2 plus, and then rewrite this again, 1/2 x plus y minus 1. Now 1/2 minus 1, I'm going to end up with 1/2 x plus y, and -1 plus 1/2 is minus 1/2. So there's my second derivative. Okay, 1/2 x plus y minus 1/2. Now, how do I know when this thing is going to be concave up? Well, now think about this logically. Go back to second derivative tells you about your concavity. Where it's equal to 0 is how you're going to find your pips, your possible inflection point. So what I did is I took this equation and I set it equal to 0. And I went ahead and I solved for y. So y was equal to -1/2 x plus 1/2. Okay? Now, this right here is a line, okay? When y is positive, then the function will be concave up, okay? So, your function will be concave up everywhere above the line because you want this to be greater than or equal to 0, okay? Because you want it to be positive. So, it will be concave up above the line. Okay? So, what did we do? We set the second derivative equal to 0 to find our possible inflection points. We didn't really find possible inflection points because we've got x's and y's, but we were able to solve for y and to get some sort of a line. Well, that meant, because remember, if your second derivative is positive, it will be concave up. If your second derivative is negative, it'll be concave down. So if y is positive, it will be concave up. Positive is going to be everywhere that's above this line. If y were negative, then it would be concave down. That would be everything below the line. And they wanted to know where it would be concave up, so it's going to be concave up above the line. All right, let's look at part C. Oh, where'd my problem go? Part C. Let y equals f of x be a particular solution to the differential equation with the initial condition f of 0 equals 1. Does f have a relative minimum or maximum, or neither, at x equals 0? All right, so f of 0 equals 1 is a point that we have. And what tells you whether you have a relative max or a relative min? Well, the derivative tells you whether you have a relative max or a relative min. So dy dx is equal to 1/2 x plus y minus 1. That's what they originally gave you. And you want to say, do I have a relative min or do I have a relative max at x equals 1? Or sorry, when x equals 0. Relative min or max at x equals 0. Well, when x equals 0, y is going to equal 1. And in order for it to have a relative max or a min, what does your derivative have to equal? Your derivative would have to equal 0. So let's take a look. If we have 1/2, x is equal to 0, y is equal to 1, well, that's 0. That's going to equal 0. So your dy dx is equal to 0. So yay. It's going to be a possible relative something or other. So now you've got to figure out if it's a regular, or if it's a relative max, or if it's a relative min. That's a little harder to determine, okay? Because you could do your number line. You could, try points to the right and to the left of that 0, but you don't necessarily know the y's. So how would you be able to plug it in if you can only plug in your x's and you don't know your y values? Well, think about the second derivative test. The second derivative test says that if something's concave up, you're going to have a relative minimum. If something's concave down, you're going to have a relative maximum. Well, when y is equal to 1, that's when x is equal to 0. That's a positive value, and you had just said that when y was a positive value, your function will be concave up, okay? F is concave up. So, by the second derivative test, okay, there will be a relative minimum at x equals 0. Okay? Why? Because your function is concave up. You already know that because your derivative is 0, that you've got a horizontal tangent line right there. And so, since it's concave up, it ends up being a relative minimum. So you're kind of using the idea of the fact that it's concave up when y is positive, and the idea that, okay, well, I know it's going to be a relative something or other, so using my second derivative test, I'm able to find that value. All right, let's look at part D. Part D. Now I had to look on the internet for Part D. Part D was pretty tough. I wouldn't have gotten it in a million years. So that's okay. Remember, if you can't answer all of the questions, it doesn't mean your 5 is lost. You can still get a 5 and not answer all of the questions. So just plug along and keep going. Remember, it's more about how many points you can get rather than how many points that you are missing. All right, so it says find the values of the constants m and b for which y equals mx plus b is a solution to the differential equation. Okay, all right, so let's go through what I did here. So I've got y equals mx plus b. So dy dx is equal to m. Because if you were taking the derivative of this, you would just get it to be m. Okay, so I went to my original equation. So my original equation was dy dx is equal to a 1/2 x plus y minus 1. Okay? Now what I'm going to do is I'm going to make this equal to m. So m is equal to 1/2 x plus y minus 1. Okay? Sorry, I'll get my thing here. All right. So if I want my slope, I think I took the derivative again. Hold on, let me think what I did here. See, I'm losing it already. Oh yeah, I did. Okay. I took the derivative of this again. So the derivative of m, which is just a number, is going to be 0. And my second derivative equation was 1/2 x plus y minus 1/2. So this is the second derivative. Okay? Now, take a look at this equation compared to this equation. Okay? If you were to add a half to that, wouldn't they be the exact same equation? 1/2 x plus y minus 1 plus a half, isn't that a negative a half? So what I did is I said 0, well, it wasn't really me, it was someone on the internet. 0 is equal to an m plus a half. So this right here was this equation, which was an m plus a half. So I was able to find out that m was equal to negative 1/2. I know, right? I'm telling you, I would have gotten this one wrong. All right, so now we've got our equation y equals negative 1/2 x plus b. So we needed to solve for b. So if I get b all by itself, I get y minus a 1/2 plus a 1/2 x equals b. Okay? All right, well, look at this equation right here. Y plus a 1/2 x, y plus a 1/2 x, and then we've got this minus 1. So if we say minus 1 plus 1, it's going to be the same as this one. So this is going to be m plus 1 equals b. Well, m is negative 1/2. So negative 1/2 plus 1 is positive 1/2, which is your b. So your b is a positive 1/2, your m is a negative 1/2. Yeah, good luck with that one. I mean, maybe that makes sense to you, and maybe you could understand it. I struggled with this one. Like I said, I had to go online, and I even had the answer that I was looking at from the AP thing. The AP answer key, like, I was following along. I got to a certain spot with them, and then all of a sudden they made this jump that I didn't understand how they made their jump. So I had to look online some more. I found somebody else's solution, and it came up with this. So again, when you guys are taking your AP test, you are not going to have time to look up the internet Not to mention, this was a released question already, so there was already a ton of information on the web for this question, which I promise you, there's nothing on the web for these new questions. They just make up new questions, new questions, new questions. All right, so anyway, at least we've seen it, right? So, there's another day of FRQs. Have a good one.